I think everybody's will welcome the last lecture. I might tell you, I noticed just a side comment that Eric had a similar comment. When you prepare a bunch of lectures and you try to get them all done before you leave to get here, the last one's always got a few more errors than the preceding ones where you had a little time to, took a little more time. Anyway, first let me remind you of what we did last time, or let me go back way far. Okay, the first lecture was Coulomb collision operators, okay? And the second one was how we get fluid moment equations for collisional plasmas. Then the third one, last time, lecture 3, the subject of lecture 3 was actually fluid models specialized for low collisionality tokamak plasmas. And in particular in that regard, the question was, well, how can we get a kind of MHD, extended MHD model from the fluid moment equations of density, momentum, and energy transport, or entropy? And then we talked a little bit about the instability constraints and the flux surfaces and currents and Grad-Shafranov equation, and things come from the standpoint of you better make sure you have ideal MHD stability, because if you have MHD instabilities, they kill you. And then on a longer term basis, or towards the end, talk about the ultimate plasma transport equations. Remember, there's timescales short from, you know, Debye shielding, move across the Debye shielding in picoseconds, and cyclotron motion on 10 to the minus 8 seconds, and collision times on the order of milliseconds, and then finally we, in ITER, want to confine the plasma for seconds. And so the topics were extended MHD model from the fluid moment equations. Extended means not just ideal MHD, but including the dissipative effects. And then ideal MHD model and its consequences, the Grad-Shafranov, so-called axisymmetric tokamak magnetic geometry, and how we use neoclassical closures to get a modified Ohm's law, not just Spitzer electrical resistivity, but a viscous damping effect in the electrons to change the resistivity, plus a bootstrap current and colloidal flow damping, and then the plasma currents and flows in tokamaks. And then finally, now then go with a rather longer analysis for how to get tokamak plasma equations. So we were going to do a little bit of remind you of last time and then switch to this one. And the magic switch is over here, and I don't trust myself, so Martin's going to. And that did it? Yeah. Okay, but it doesn't show up on here. Well. Okay, that's fine. Oh, I'm going to play the game. That's okay. Okay, so today I had a rather auspicious title, Tokamak Plasma Transport Modeling, but actually I'm only going to tell you about one major subject that's been happening over the last 10 years. And the basic idea is that for many years in the, let's say, 70s, and 80s, people were so concerned, the focus was fusion. How can I get the energy containment time to be long enough? I'll hold the plasma long enough, etc. And so transport equations, people only looked at density transport and temperature transport. And this prevailed mostly through the 90s. And then starting about a decade ago, we began to see evidences. We had sort of looked at the rotation, toroidal rotation. If you may remember, we got a toroidal rotation equation, which I'll come back to, a toroidal angular momentum density evolution equation. People didn't really pay attention to it. Two things kind of happened. One was from the 90s and into the 2000s. It turned out that if the toroidal rotation changed, that your stability, your ITG turbulence and your ion temperature gradient that you could build up in the plasma changed. And so people said, well, maybe we need to worry about this. And so the way you changed the toroidal rotation was the torus is here. You did what we call tangential injection of an energetic neutral beam, and it causes the plasma to just rotate more and more toroidally. And roughly speaking, what people decided happened was that if you look at this toroidal momentum equation, there's a bunch of terms, and when you up the external momentum sources, you needed something to balance it. Collisional effects were too small, and so the microturbulence from the ion temperature gradient instabilities done now by these codes that Eric Sonadricker was talking about give you a Reynolds stress from the fluctuations. And then these two terms balance. What then happened is that people, beginning a little bit after 2000, began to find that, well, you know, we didn't build tokamaks super perfectly. That is to say, they aren't really axisymmetric. For example, in ITER, there's supposed to be 18 separate coils that produce the toroidal field. So that gives us what's called toroidal field ripple. Also, things were always a little skew. I mean, there are engineering tolerances of, you know, a few millimeters or something. And so you got various field errors, as we call them, resonant or non-resonant on the fields. And so over the last decade, there's been quite a lot of emphasis, at least in some experiments, like some of them in the United States, to figure out what actually do these 3D magnetic perturbations do. And what they effectively do, as I'll show you through some examples with too many view graphs today, is they create what I'll call neoclassical toroidal, what's become to be called neoclassical toroidal viscosity from magnetic perturbations, or the resonant field errors. And I really won't talk about these, but they all contribute is the idea. This subject has an advantage. Most of the time, you look at the turbulence and it's there, and you manipulate some things to change it. But pragmatically, it doesn't really, you don't have direct control, you have trouble measuring it and its effects and so forth. Here we will introduce extra 3D fields. And the question we ask then is what does that 3D field cause in the plasma? And so it turns out that we're going to show that actually you can manipulate the toroidal rotation, omega t, frequency, that's how fast the whole plasma rotates toroidally, and only indirectly through changes in the turbulence typically do you change the electron density, temperature, and ion temperature. But really, you know, we write down this equation and we have, remember, 8 ambipolar particle fluxes and 8 non-ambipolar, et cetera, et cetera. We have lots of processes going on. In this case, with the 3D fields, we separately introduce something and we say, how can we manipulate the toroidal rotation in the plasma? So, and then finally, I'll come back to, as I mentioned at the end of the lecture yesterday, how are we going to get a grand unified toroidal simulation? So today we'll talk about, I'll talk mainly about 3D fields on the rotation by acronyms. I can't remember who said, we really like acronyms in magnetic fusion. I have to tell you a side story. Acronyms are very common in various fields. One of the fields they're very common in is fission nuclear engineering. And there was a certain woman who took over the Department of Energy, which has the fission nuclear power in the United States. And she had a small piggy bank on her desk. And for anybody who came in and gave an acronym without telling what it was, they were forced to contribute a quarter to the, to the piggy bank. One never ever found out how much money she made on this, but we love acronyms too much, okay? Anyway, so I'll try to tell you about these various effects on various types of magnetic fields, and then the role of the okay, we're going to introduce extras, and then if you have some instabilities that grow in the plasma, some fluid-like magnetohydrodynamic extended MHD modes, then they can affect the plasma responses and everything. And then I'll tell you a little bit about something called a flutter model, which is kind of intermediate between kinetic and fluid approach. And basically try to emphasize just that there's lots of these, and then how are we going to maybe pull all this together. So this is just a reminder of the density, momentum, and energy or entropy conservation relation. And where 3D fields fit into this is that if you look at the momentum equation, you've got a J tilde cross B tilde. Now, in an ideal MHD plasma, there is no toroidal component of J cross B. J cross B is grad P is only radial. And so there's none. But if I have various types of perturbations, then I can get neoclassical toroidal viscosity, as we'll talk about. And Ripple does it, and resonant magnetic perturbations give it to you, either by a J cross B or a divergence of a stress tensor. And notice that those aren't really involved in particle fluxes directly and so forth. So in some sense, you can play with the toroidal rotation somewhat separately, I guess is the way to say it. And then you can have spontaneous magnetic perturbations in the plasma because of extended MHD modes, neoclassical tearing mode, resistive wall modes, we'll briefly chat about later. Okay, so what kinds of 3D effects do you get? Well, in a magnetic field, in a tokamak, to lowest order we say it's axisymmetric. Maybe I'll say that more on the next slide. And then we expand in the Fourier series in the only ignorable coordinate we have, which is toroidal symmetry to lowest order. And so we expand about that. The low toroidal mode numbers tend to give us, if they're non-resonant, this damping of the toroidal flow, a direct damping, it turns out. The medium, we have 18 coils being built in ITER, so that's n equals 18, you know. And then we also have low n resonant ones. What that means is you take a field line and go around, and if a field line bites its tail after, say, 2 times around, that would be an m equals 2 situation, 2, 1, then you're resonant. So if you apply a magnetic perturbation which is resonant with that, so that you effectively put a magnetic perturbation on that's helically resonant, then it's going to interact only on that rational surface, which is, say, halfway out. Here's a pressure versus radius. For example, halfway out, you might have a Q equals 2, 1 surface, and you might have a Q equals 1, 1 surface here, and maybe a 3, 1 here, and so forth. So if you put on an external magnetic perturbation that is resonant with a field as a function of radius, here's my little tokamak, someplace resonant in the plasma, you can interact with it. Now, we already talked about all the colloidal flow and everything, so I won't repeat that. So here's the information that's over on the graph over there, just for as we go through things. So the basic idea is the lowest order to lowest order, we do solve the Grad-Shranoff equation, we get the magnetic field as a function of poloidal flux, a radial coordinate, or rho. And then we expand in a Fourier series. And we have low m's and n's, both resonant, where m is, you know, m theta minus nq turns out to be nearly 0. And so if a particle is following a field line are resonant with that extra component all the time. Or non-resonant, it's sort of like it's a backward helix or something like that field. And then we have that around the toroidal direction, because we have 18 coils, the magnetic field is going in and out. You know, it's just a little bit bumpy, and we call that ripple. And then finally, everything that's higher order, so n greater than 10 or 20 or something, we just say, oh, that's Eric's problem. That's microturbulence, okay? And so far, we tend to treat these as totally separate subjects. That is to say, all these lower order magnetic fields are kind of what I'm going to be talking about. The microturbulence is a completely different set of codes. And ultimately, we're going to have to get this together. As I had mentioned last time, on the microsecond time scale, compressional Alfvén waves enforce the radial force balance. And what that turns into is it says that toroidal rotation is related to the radial electric field and two diamagnetic flows. And so the toroidal field is toroidal rotation velocity is approximately the radial electric field divided by the poloidal magnetic field, the twisting, and two diamagnetic flow type things. And then we had gotten, by forcing radial current to be zero, we'd gotten a momentum equation, which I've written over here in a slightly different form than we did before. So now let's talk a little bit about these terms. So first I'm going to talk about what's called neoclassical toroidal viscosity from magnetic perturbations. And so the idea is, you remember we had so-called poloidal. Poloidal's the short way around in a tokamak. Damping by the plasma was moving along field lines from the outside to the inside, and the collisions just kind of relaxed that. Okay, it said, no, you can't do that. I want to relax that flow, and so forth. Now, in a tokamak, to lowest order, it's actually symmetric. And I've got this, I guess, on another slide. Oh, yeah, no, it's at the top of this one. This is getting me a little bit, and I'll get used to it. What's happening is that if I have, just think again of flow down a pipe that's bumpy. If the pipe has no bumps, and we have no bumps in the toroidal direction, then I'm just free flowing, okay? But now, if we introduce these 3D bumps, particularly the ripple, but also twisting of field lines, because that makes it do the same sort of thing, then you can show, and that's a lot of detailed mathematics of a kinetic nature, that the toroidal component of the viscous force is a damping frequency, which is quite small actually. Well, it's fast, but the combination with the magnetic perturbation level is fairly large. And it's some frequency, so it's just a damping. This will just damp the flow, but with some offset. And so we're going to show in a second the viscous damping coefficient. And so the toroidal rotation in equilibrium, when you get to equilibrium, it should be some electric field, diamagnetic flow, and an ion temperature gradient with Ki, a special number, 1.17, things like that. And the shift frequency here is the C sub P plus C sub T. Everything C is with small numbers under them are just what I called earlier headache factors. You do a long detailed calculation, you get 1.17 instead of 1. But anyway, you have to do that to get things right. I might say my colleague Kerchung Shang at the University of Wisconsin now, he was actually a postdoc with me, he's done perhaps 50 papers on various aspects of these, actually he does it as a particle flux, and we convert it, non-ambipolar particle flux, and he converts it into a viscosity damping coefficient. But the key thing is, when you're a fluid mechanics person, or frankly in most extended MHD codes, you put in an isotropic viscous force and viscous stress. Okay, that means there's no directionality to it. But as all the lecturers have been emphasizing, all the magnetic ones, have been emphasizing, you know, we got very fast along the field line, slower cross, and very slow radially. So if I put in an isotropic viscous damping, all that happens is that, you know, the flow's down this way, and it just kind of diffuses radially. You diffuse the momentum radially until you get to the boundary and so forth. But you remember, a tokamak is intrinsically very anisotropic. So what happens is actually you get a direct drag on the flow. And again, it's this analogy of flow in a bumpy cylinder. If there are some bumps, even small bumps, these are very small bumps, 1 part in 10 to the 3. 10 to the minus 2, 10 to the minus 3, there, 10 to the minus 4. They're actually small bumps. But because they're a symmetry breaking bump, they're going to give us a drag on that toroidal rotation. Because by symmetry, we didn't have any axisymmetric. We didn't have any toroidal component, covariant base vector, but anyway, of the viscous force. But this is just a regular drag. So if you look at my momentum equation here, if this was the only term, this would say that you'll have the toroidal angular momentum damped because of this. It'd just be minus mu delta B squared on the frequency, and it would damp it to an offset frequency. And what I'm going to show you is some data. The number of experimental colleagues of mine have come up with, whereby they've shown this really works, okay? Really works in the standards of, of experiment and theory comparisons, which are, you know, tens of percent typically in magnetic fusion. You know, in atomic physics, it's 1 over the fine structure constant, 1 over 137. Atomic clocks, it's fantastic accuracy. We're down at the 10 or 20%, maybe 30% level. Anyway, so what I want to tell you about is a little bit of this. So first comment is it's calculated from actually, okay, I'll get to this in a moment. But anyway, let me just skip this slide because I remember I diddled, I put it. So in 2D axisymmetric situations, Professor Rax had this on one of his graphs, as I recall. You take a particle and you go along a field line and it goes back and forth, and because it's moving a little bit radially, okay, you look at it and you think, oh, it looks like a banana, turns out, if you're in a certain projection. But now, if we add a three-dimensional field, an extra field, where it turns is a little bit different. And so what happens is the center of this banana walks out or in, depending upon what phase you are relative to the toroidal magnetic field. So we call that a banana drift. You know, it goes up and back, but it's going out or it's going in, and it's called a banana drift. And so we have to calculate the mathematics of that banana drift. And then if collisions are sort of medium level, then they will limit, I can go for a while on this, and then collisions decorrelate me and I get a little transport, but they quit going. However, I can have other situations where I get a boundary layer at lower collisionality, and then it's determined by 1 over the toroidal rotation frequency due to the radial electric field. And then finally, if that radial electric field is very small, then the bananas might go for a while until the electric field changes, and then they go back and forth in that electric field radial well, the centers of the bananas, and that's called super banana plateau, it turns out, but anyway. Now, almost all of these effects, until I get to flutter, almost all these effects are ions. And so what's happening is the ions are executing these motions. And so it's not an ambipolar process. It's a non-ambipolar process because it's only the ions. The electrons are not doing anything. So this will tend to create an electric field of a certain sign. Namely, it turns out a negative electric field throughout most of the plasma. And to the extent that you have more of it, it goes more negative. Or a toroidal, the toroidal rotation turns out to be in the same direction as the anti-direction of the beam. So the beam is injecting momentum this direction, causing the plasma to rotate this direction. This process causes it to slow down a bit. It's so-called counter rotation, counter to the current direction, it so turns out. So now, this is the graph that causes my Acrobat on my computer to go bananas and quit. You know, it says, you're a bad boy, can't do that. Anyway, so mainly this Kerchungsang, but with some other collaborators, myself and so forth, a number of others. He's developed a diagram, and by the way, he's writing a review paper for nuclear fusion that should be published in, I don't know, 3 to 6 months. It's only a 200-page summary of all his calculations. And I've tried to sketch it here, and I kept it here for reference, so to speak. So the idea is this diffusion coefficient for non-ambipolar flow of ions across the field depends upon collisionality. High collisions, they don't go very far. Low collisions, they go a long ways. As a function of, this is the diffusion coefficient, and you can convert that diffusion coefficient into a viscosity toroidal, neoclassical toroidal viscosity frequency, which is of the order of a second or so for ITER, it turns out. So if you look at the ion diffusivity as a function of collision frequency, when you do regular axisymmetric neoclassical transport, by the way, classical means you get particles that are gyrating, they have collisions, they jump a gyro radius. Neoclassical means they do that, but they also do their banana motion, and in doing so, they drift off the surface a little bit, and so that's called neoclassical in a particle sense. In a fluid sense, neoclassical means that I'm moving along the field line and I get these viscosity effects that we talked about last time. Anyway, so ordinary axisymmetric magnetic fields have a Fierst-Schluter or collisional-Brzezinski regime, a medium plateau it's called, and a banana regime where you execute a whole banana and then you have a collision. This is very low collisionality physics, which is only available in present machines over the last decade and a half or so, and certainly will be true in ITER. And the gist is that the diffusion, or as I wrote it, as a viscosity coefficient frequency, as a function of collisionality, looks like this. It has various regimes. The key point that I will want to get to relative to experimental data is, one, that all this process is doing is, again, it's flow down a pipe, and it's like a bumpy pipe, and so the drag is on the whole plasma. And notice that it depends upon various frequencies. Suppose I had a situation where the electric field was 0, then this particular, or very close to 0, then this particular frequency moves down into this range, and you get a huge viscous damping, or diffusion, a non-ambipolar diffusion, or alternatively, viscous dissipation, or torque on the plasma, neoclassical toroidal viscous torque. Again, with this form of basically this second term there, that one right there, is just of the form of a drag on a toroidal rotation frequency. So you might say, hey, does this all work? And the big thing over the last decade is people have actually done measurements. Oops, that one will take time to undo. Oh, so this is a ugly graph, multiple regimes and all that sort of stuff. And so we had to develop, turns out, a smooth formulas. Okay, when you're a theoretician, you work, 50 or 100 pages of algebra, you come out with some complicated formula, and you go to your experimental colleagues with this nice big complicated formula, and they say, well, kind of give me a formula for if I'm right here and increase this variable by a factor of 3, how much does stuff change? They mostly are dealing with only simple things. So we had to come up with a simple form for that. Simple. Anyway, the toroidal rotation sort of was singular, tended to be singular at that low frequency regime, unless there was enough collisionality or enough grad B drift and stuff like this. Now, so what you'd like to do to validate this theory is you'd like to say, well, okay, I have a tokamak and I will apply a toroidal torque on the plasma. I inject a neutral beam, it's absorbed, its momentum is imported into a toroidal torque on the plasma. And I'll ask, do field errors or I'm sorry, these non-resonant fields, I apply a 3D field, and how much does that change my rotation? And so this was done in NSTX experiment at Princeton Plasma Physics Laboratory. And, well, it was actually done a little bit there had been money indication before, but this was a clean demonstration. So they measured the experimental torque when they applied the change in the torque when they applied the 3D field. And the measured torque was this, and the theory was that. This is actually for a so-called n equals 3, so toroidal mode number of 3 perturbation. And the idea is that this is considered pretty good experimental comparison, okay? However, they then did also another experiment. This was a non-resonant one, so the real field lines are twisted like this, and the perturbation was, had the opposite helicity, so it was not resonant. Then they said, okay, let's try the resonant case. And then the theory, if they did the applied field only, was too low compared to the experimental data. However, if they took account of the fact that when they apply this magnetic field, the plasma actually has a response, and it actually amplifies the magnetic perturbation in the plasma relative to what it would have been by vacuum. We call that resonant field amplification. And so out of that, and things that I'll come back to later, what we have later figured out, and I'll come back to this, is that if you have a resonant perturbation, then the plasma has a response, which is effectively you have a driven damped oscillator situation. You have your natural n equals 1 kinks in a tokamak are only a little bit stable. Remember, I couldn't allow kink modes because that would have been violently unstable. So you arrange the pressure, current profiles, and Q profiles, and twist profile, field line twist profiles, so that you're stable. But you're stable, but only a little bit stable. You've still got a residual mode there, which if you excite it, it will amplify a little bit just because you're driving it. It's externally pumped, otherwise stable mode. And lo and behold, that effect is what gives you about a factor of 2 here. It can be actually factors of 3 to 5 or 10 in real plasmas. So that was pretty encouraging. Now, Another thing about this diagram is if the electric field goes to 0, which is tied by these formulas actually to the rotational transform, then you would say that this toroidal rotation, it may be being damped to a certain rotation frequency, but this mu is getting very big if the electric field vanishes. Well, there's two features. And even if you stay away from that, go into this regime, this formula says it should take this effect, big 3D field, should cause the plasma to rotate down to a certain offset frequency, which is actually, it turns out, in the so-called negative direction. So a certain colleague of ours at General Atomics D3D, he believed us theorists. Hey, okay, I'm going to test you, okay? So what he did was he took the tokamak in D3D, and he had not just one direction beams, but he had beams that he could counter. And so he could say, I'll run the momentum this direction, and I'll run the momentum that direction. What would you predict from this simple relation as that being the dominant term in your toroidal angular momentum? Well, it says that the plasma will try to go to an offset rotation. If I'm going in the co-direction, it should slow it down to that in the offset. If I'm going in the counter direction, it should go up to that. And lo and behold, he was able to demonstrate that. So here's that diagram on the left. And the idea is if he started out with a positive co-rotation, we call it, then lo and behold, any co-rotation tried to go to this band, the offset rotation, which was within factors of 2 or so of what we predicted where it ought to be. And if you started off with too much negative, you know, you're going the wrong direction, it actually increased up to this. The second thing is there's this peak. And if you somehow arrange the electric field to be nearly 0, then it turns out that your banana orbits walk way away and come way back. And at a very low collision frequency, you ought to get a lot of torque. And lo and behold, the torque they measured as a function of toroidal rotation frequency peaked right around this -5, -3, -5 kilohertz, kilorads per second toroidal rotation frequency. Now, theoretically, we're still having problems with the fact that we're sort of, yes, the peak's here, but we're not as broad as they are. And we think that's insufficient physics and pitch angle scattering, kinetics, and so forth and so on. But anyway, generally speaking, the idea is that we think that some process like this neoclassical toroidal viscosity caused by 3D fields is just a direct drag and so forth. It has now come to be in tokamaks that they believe in it so much that if they don't like the rotation profile they're getting, they turn up the 3D fields to cause it to be something different. And they can manipulate it. And they run various experiments to do that. So we consider it mostly a success story, although I have to say there's details. Okay. Next subject. So that's basically this delta B, the low n. Now let's go to the medium n. So again, ITER plans on 18 coils. Jet and D3D Jet has 32. D3D has 24. Anyway, you get little bumps around the toroidal direction. So the toroidal field's doing this. Well, if the toroidal field is doing this, you go into the detailed particle orbits, and it turns out ions just jiggle back and forth in those magnetic wells along field lines, and they drift out of the machine. And so again, non-ambipolar particle loss. And so the theory goes through the very same, and you get again, a neoclassical toroidal viscosity damping. And so anyway, there have been various levels of this, and I guess it's been done in device I used to work on a little bit, ISXB at Oak Ridge National Laboratory, JT60U in Japan, JET, of course, in England, Tor Supra in Cadarache, and so forth. And the basic idea is it's a similar type term as this. And so they did some experiments. And so here's the toroidal rotation profile in the JT60U experiment as a function of radius. And basically it happens to be in this, I'm confused about something, but anyway, they're in the opposite direction. So anyway. So they're creating a positive change in the toroidal rotation. Now, there's something subtle here that's kind of important for real designs of like ITER. ITER's only going to have 18 coils, as by the way JT60U did. And so again, the magnetic field is sort of rippled. If you have too much ripple, what could you do about it? Well, you're not going to build more than 18 coils. I mean, you bought those and they were half the price of the machine. And we don't know what the half is of what number, but anyway, we know it's a big number. And so, but what you can do is you can put ferromagnetic inserts between the coils. That's what's called FST, ferromagnetic steel tiles. And so basically, with FSTs, without FSTs, you get a counter negative effect of the field coils on the toroidal rotation. But when you compensate by a factor of 2 or so in the field ripple, you end up causing the toroidal rotation to go up. A more systematic study that was made possible in JET, Gabriela Sabina did this. In JET, like I said, they had 32 coils. And usually you run all 32 coils full blast. But what she did is she said, well, let's power every other coil at some intermediate amount, so she could vary the amount of field error or of ripple on the edge for an n equals 16 system effectively. And so when she did that, if you you could change, okay, 0.25% was, it's very hard to read over here, but the highest curve here is the lowest they achieved, all 32 coils working. But then as they dropped out coils, the plasma tended to be slowed down in the toroidal direction. Here's the toroidal rotation frequency in the edge where the field ripple's biggest. And so again, we think this has worked out right, and actually the people who did this did some further analysis, nice quantitative analysis, and it seems like the theory we have is working pretty well. I was at ITER last Friday and had an entertaining discussion with the people there. And it turns out that they're at about 0.5% with the 18 coils in ITER, 0.5, 0.6% ripple. This is 1 part in, or 6 parts in 10 to the 3. You put in these ferritic steels, inserts. The kinds of discussions they're having on ITER are the engineers are coming back to the scientists, physicists, and saying, hey, look, we're trying to put these in, but they're getting big torques on them because they're J cross B forces, and we're afraid they're going to fall off. So we'd like to make them a little smaller so they wouldn't have so much torque. And the physicists say, no, you don't understand. We can't let them be smaller. Or, well, anyway, so they have a dialogue, well, could we get by with a little bit here or there, that sort of thing. And so it's actually you know, the theory and experimental validation is compelling enough to make this an issue, so forth. So, okay. So now, I've kind of not directly talked about it, but we have these low-order field errors. So you build a device, and you have typically 1 part in 10 to the 4 of a resonant perturbation, okay? And what happens? Well, it turns out that it causes what's called a locked mode, and I'll show you a picture of that later, but the gist is that on that rational surface, like say the 2-1 surface, it causes the toroidal rotation there to be locked to the wall, no toroidal rotation, and the rest of the plasma is still flowing toroidally. And then over a period of time, the viscous force or viscous diffusion causes the momentum to flatten over the whole profile. And okay, we have to get into one other thing. If you take a copper bar and you impose an electromagnetic field on the outside, it goes in on a resistive time scale. Now suppose I have a superconductor. Then I apply a magnetic field on the outside. It doesn't get in. In a similar vein, in a tokamak, you have a plasma flowing toroidally, and actually the typical electrical resistivity of a tokamak at the 2-1 surface is 10 to 100 times better, lower resistivity than a copper bar at room temperature. So what happens is that the plasma, as long as it's rotating, it turns out, it looks like a superconductor and it shields out all these perturbations. So if you go back historically in the early tokamak experiments, man, they were rotating like mad. And so you never had any problems. Well, in the more recent tokamak experiments, they've gotten hotter plasmas and better techniques and all kinds of things. And they're not rotating as rapidly. And ITER, by the way, is not supposed to rotate very fast at all because they have weak beams compared to the size of the plasma. Is kind of what it amounts to. So anyway, you end up with a situation where Fitzpatrick, a guy named Richard Fitzpatrick, Callen / University of Texas, Austin, has built a nice cylindrical model, and it's been verified in toroidal codes. But anyway, the idea is you get shielding or screening of these field errors if the plasma rotates fast enough. But if the plasma starts not rotating, then you have the problem that the field error penetrates. It causes a magnetic reconnection of field lines on that rational surface, usually a 2-1. And actually you get a growing island, and you sometimes get disruptions. So what happens pragmatically in present tokamaks is they start having this problem at low density as they're building up an ohmic tokamak, and they say, well, I know how I can make that tokamak rotate. I'll stick in a neutral beam and I'll make it go and rotate. And they do that. In ITER, that beam's not very powerful compared to what's going on in the plasma. And so they worry a lot about field errors, and they build extra coils to compensate. You know, it's sort of like a field error means I couldn't figure it out when I was building it. And they, you know, they try to adjust everything to sort of millimeter scale. But you're going to end up with some error. And so what they actually do is they put on extra coils that they can compensate for the field errors that they didn't know were going to be there, or they couldn't quantify, you know, because you build within a certain millimeter tolerance and you're still getting errors, but one's a little bit different than the other. So they have compensating coils, and they're inside the vacuum vessel, it turns out. So anyway, there's been some, so they build these compensating correction coils. The only problem with that, which is a current topic of interest, is you got the field error and you compensate. Fine. Now you turn on the plasma and you can increase the plasma beta, or you increase the twisting of the field lines. And lo and behold, the plasma response changes. So your field inside the plasma is no longer that which you had because of a vacuum, but it depends on the plasma pressure and current. And so now you need not just a compensation of the field error, but a dynamic compensation of the field error, that as the plasma pressure and twist of the field lines goes up, you adjust it. And they're actually working on experiments these days which are very beautiful and can dynamically do that as they're building up the plasma. So it's an interesting subject. Okay. So in this particular case, what happens is you don't get this NTV delta B, but you get a resonant field error. If you had an axisymmetric tokamak, there would not be that term because J cross B would be grad P would be radial, and this is the toroidal torque. So, it'd be the toroidal torque of a grad P. Grad zeta dot grad P is 0, basically. There's no, everything's constant in the toroidal direction, except for the bumps, and this is the bumps. And it only happens in thin layers around rational surfaces. Okay, so anyway, Fitzpatrick's worked out this theory, and it goes like Alfvénic speeds with magnetic perturbations. And this is, if you rotate fast enough, this is the screening factor, and it's effectively a delta function at whatever your rational surface radius is. And anyway, so if you rotate fast enough, no big deal. Don't rotate fast enough, these things can grow. So control of these becomes an issue. And here's a demonstration of some of this. And the idea is that the magnitude of the perturbation, Gauss per kiloamp, Gauss in the plasma to kiloamp in the coils, the field error correction coils. And the idea is that lo and behold, it just goes up linearly as beta, the plasma pressure goes up, but you actually start getting a divergence of it. You get a plasma response, but the plasma response diverges as you get close to what's called the no-wall limit. Maybe I should mention that now. Okay. Usually in a tokamak plasma, we draw this, but we have a shell there someplace. And if the plasma kinks, and if that shell, as in the case of T3 in 1960s, the edge of the T3 tokamak physically was about this big, was a about 4 or 5 centimeter thick copper shell. That was a fixed boundary, conducting boundary shell, okay? So if the plasma started to kink, we get an image current that'd fight back and it'd say, no, don't do that. Or, you'd be hard pressed to get an instability. Since that time, we have gone to free boundary equilibria, where we, get these diverter separatrices, and we put, shells around it, and then we put colloidal field coils, and it's a free boundary equilibrium. So theorists define 2 interesting beta limits, or pressure limits. One's called the no-wall limit. No-wall limit means that if you don't have any wall, there's no copper shell around it, then that's your pressure limit. They would like to go past that, okay? But these things show you that this is the no-wall limit. This is beta over beta no-wall. When you go past that, experimentally, it turns out you can. It's a little better than the calculations show, and that's because of resistive MHD and wave-particle interactions, resonances, it turns out. But anyway, you get into this, I would like to be over the no-wall limit is the idea. And these calculations were insufficient at the time to calculate that properly. They were, Mars F is a 1-fluid resistive MHD code as opposed to 2-fluid with kinetic effects, but anyway. Okay, so now, up until now, in this 3D effects today, I've been talking about we apply an external field, or we have field ripple, which is externally imposed. But, you know, we have a lot of things going on. So the first thing, as I mentioned earlier, is that any delta B that you apply, if it's resonant, it couples to the least stable mode in the plasma. Least stable means it's most weakly damped. You get higher modes that are more weakly damped, but if you could couple to the least damped mode, you can amplify it the best, easiest. So we have to worry about that plasma response, and those are being estimated by various codes. Then the second thing is when you go up to high enough pressure and you get a big bootstrap current, you can get what's called neoclassical tearing modes. And the idea there is you start making magnetic perturbations in the plasma from the collective responses of the plasma. Similarly, you get what's called resistive wall modes. When you're above the no wall limit, you've still got a little bit of a wall there with a little bit of resistivity. And so you can get resistive wall modes, as they're called. Anyway, these are self-consistent things that happen. Then, and I'll come back to this later, if I draw a pressure profile like this, and I tell you that as a function of radius, so this is the center of the tokamak, and this is the separatrix, okay, row of 1 is the separatrix. If I draw a pressure profile like that, and I tell you that the biggest instabilities in these plasmas are driven by pressure gradients, where do you think I'm going to get an instability? Right there, okay, in the edge. And sure enough, we get something called ELMs, edge localized modes. And what they've basically done is they said, and I'll come back to this in greater detail, they said, well, let's put in a whole bunch of resonant modes out here, and we'll try to control this pressure gradient out in this region so that I don't get those instabilities. Now, well, anyway, we better go back, go to that later. Let me just put it this way. Okay, so they're trying to put on extra fields to control these edge localized instabilities. And anyway, and these 3D effects, as I'll show, mainly affect the toroidal rotation, not field error, not the density and temperature. And so we'll try to go through a few of these things. So now, suppose you apply an external magnetic field, and you would really like to couple to the 2-1 surface because, you know, I'd like to counter the field error that's going to be there. How do you construct the external magnetic field that you apply to be able to affect things at that surface? Well, you know, as a theorist, and you say, hey, it kind of looks like a cylinder to me, why don't we apply a 2-1 mode? Turns out that's not the right answer. Because you're going to couple to the least stable kink mode. And the least stable kink mode may be a toroidal mode number of 1, but in the core of the plasma, down in the core of the plasma, it might have an M poloidal mode number of 1 or 2, but out near the edge, the Q value, the M over N, is up to 6, 5, 6, 7, 8. So lo and behold, people have done studies and they said, well, the magnetic perturbations as a function of radius it may well be by this blue, the M equals 1 component may well be in here, but as you get out towards the edge, lo and behold, it's an M equals 6 or 7. And so this was a strange thing. People said, gee, I'm applying a 2-1 mode, or 2-1. Why isn't it coupling well? Well, they had to redesign the type of coil that you put on to manipulate things to have all the wiggles on the outside and have high poloidal mode number ripples. And so they've really found that in order to affect field errors, they need things that are, to me, started out as counterintuitive. That is to say, again, that they're coupling to the M7-1 mode out here in order to affect the 2-1 mode, the green curve in here. But that's because the eigenmode is an eigenmode n equals 1, but poloidally the structure is lower m in the core and higher m in the edge. These are just subtleties. Well, okay, I should have had this earlier, but usually, you remember we had a magnetic perturbation formula, dB dt, and ideal MHD is curl of V cross B. But you can work that out as a delta B then is a curl of the how much radial motion C in a virtual sense moves relative to the magnetic field, and the radial component of that delta B is B dot del times that radial virtual perturbation, and B dot del is this M minus NQ resonance. So in ideal MHD, this resonant perturbation, if you apply resonant perturbation, it's as if you should produce a delta function current on the rational surface. You add a little bit of resistivity, viscosity, neoclassical viscosity, and you get actually a reconnection of field lines on those rational surfaces. And so that's kind of how the theory of this goes, and I'll be way behind if I don't ignore some of these. Anyway, so the direct effects of instabilities in the plasma that may be controlled is still they're producing 3D magnetic fields. And as I mentioned last time, neoclassical toroidal viscosity, or neoclassical tearing modes, a particular type of them, can actually produce magnetic islands in the plasma. They grow, you don't like it because they hit the walls and then cause a disruption. And again, if you rotate fast enough, the plasma effectively is a superconductor, and so it shields it out, but with you get this amplification type things. And all of that increases the neoclassical toroidal viscosity damping, and you become more and more sensitive to low-end field errors, and in addition, you tend to excite neoclassical tearing modes because they also have the same properties. So anyway, then there become questions of, well, what's the threshold beta you can get to avoid as a function of rotation and as a function of the plasma perturbation at the rational surfaces. And anyway, recent experiments have shown, yes, there's issues there, and they hope in ITER they will have enough rotation that they won't have these problems. Now, this is a hodgepodge screen. This is actually a graph I made up a few years ago, 3 or 4 years ago. And 3 or 4 years ago, we were having real trouble understanding. We apply resonant magnetic perturbations that are resonant at this region of the plasma. And let me just say, there were lots of various types of theories that might be applicable, okay? And at that time, what we could conclude was more or less, yes, these 3D fields effects are having an effect. The experimentalists told us they are. They could stabilize these edge localized modes. But the types of theories that were being done were just all over the map as far as possibilities of what was going on. So many people have been working on this, and I'll tell you a little bit about some of the developments, one of the particular ones I've been involved in, to illustrate the kinds of effects you need to perhaps take account of. So first, let's look at what actually happens experimentally. So in some sense, if you have a pressure profile, oh, by the way, there's a matter of terminology. So the pressure as a function of time in a tokamak, when they used to do this back in the early 80s, they would turn on the neutral beam heating and the pressure would go down. Okay, turn off the neutral beam heating and then come back up. And on the other hand, ASDEX came up with a mode of operation which when they turned on the neutral beams, the pressure went up. Hey, that's what we want, right? Not that we're pumping things out faster, but you know, we're actually going up. And so he called this the H mode, high mode of operation. And when you would ask him, Fritz Wagner did this, you would ask him, you say, well, look, this is the high mode and that's the low mode. And that terminology or acronym or whatever has survived to this day. When you get an H mode, this is what the profiles tend to look like. If you had an L mode, as it's called, they would look more like this. The edge wouldn't have this pedestal, what we call a pedestal. So I collaborate with some folks at D3D, and here's a picture, which, by the way, the experimentalists don't like, because you take a look at the pressure profile here, and that when here was the dotted line here was the pressure profile in the edge, okay, and here you see the steepest gradient, but anyway. And they killed the pressure in the core by a factor of 2 when they applied these RMP, resonant magnetic perturbations. They don't like that because the ITER guys say, I can't accept that much change, okay? But as a theorist, you go and you look and say, hey, I'd like to make a comparison with my theory. And you don't like 5 or 10% effects because they're in the noise. You want something robust where you really cause an effect. So here they did. Here's the electron temperature profile towards the edge. And here you see the kind of pedestal. And I'll call an edge region a pedestal top and kind of going into the core. And before you had this profile, so you had a nice pedestal. And after you turned on the RMPs, which are the with blue, you flattened the temperature profile in this region, or in this region. Particularly about there, you change the density gradient, or the temperature gradient, and actually the density gradient, rather substantially. And so what's happening is that you then, because you're changing, then this is density, temperature, density, and so pressure, that's supposed to be a P. You clearly decrease the pressure gradient in this region. And there were these edge localized modes, instabilities that were happening in the edge otherwise. And what they are is they're periodic bursts, or nearly periodic. And what they tend to do is they tend to cause the profile to look like that. It sort of goes down here and up here. And what they do is they deliver the outer 5 to 10% of the plasma onto the diverter plates as a pulse of energy. And in present machines, this is not a problem. In ITER, they say, we can't stand that much of an energy deposit. And so present experiments, they only deposit of the order of 100 kilojoules at most. ITER, the predictions are they can only stand about 1 megajoule in a pulse. And pragmatically, these pulses are predicted in ITER to do 30 to 50 megabytes, or megajoules. So there's presently a big effort to say, can we understand why and how these RMPs, resonant magnetic perturbations, cause the pressure gradient to go down a little bit by the coils, not by instabilities. And so there's an impetus to try to understand that. This is a heat diffusivity, a radial heat diffusivity profile, which you have an edge barrier, transport barrier, low chi region. And when you turn on the RMPs, you up it by about a factor of 6 or so. Now, all of these RMP effects, like this one, they go proportional to the magnetic perturbation squared. So one of the first questions you ask for experimental sort of, validation is you say, well, I'm sorry, I need to go back to a history here. So the original idea in the RMP, particularly by a guy named Todd Evans, but it's an international consortium of some people from Australia, some people from JET, some people from ITER, and so forth and so on. They came up with this idea. They said, well, look, what we're going to do is we're going to make all these resonant fields cause little magnetic islands around their rational surfaces, and we'll have them overlap, and they'll create stochastic fields. And then that'll, stochastic field, then there's not as good a confinement. Transport's very rapid across that region. Rochester-Rosenbluth, it's called stochastic diffusion model. But it turns out that, and it explains some key things. However, the electron transport, oops, sorry, I went the wrong direction. I see. Okay, so the idea was that, gee, it didn't go flat. It just, got a steep, weaker gradient. So the chi went up by a factor of 7, but it didn't go up by a factor of 100, which is what was kind of predicted. Oh, I'm sorry. So anyway, I wasn't going to go, I was almost going to go backwards. We don't want to do that. So anyway, so then you get parallel heat conduction along wiggly field lines. And what you can say is, well, if you were totally collisionless and very fantastic, or very, very, very low collisionality, fantastically large parallel heat conduction, temperature would be constant along a field line, et cetera, you wouldn't get any transport. But really, there's finite transport along field lines. And so we ended up developing what's called a flutter model, and taking account of collisional effects. And basically, it says that the radial chi-e due to the magnetic perturbations is the parallel effective trap particle effects, et cetera, along field lines a la Brzezinski, but just modified for torus, and times your magnetic perturbation. And we developed cylindrical toroidal models. And when you do the mathematics and you have to do kinetic analysis, we used a Lorentz pitch angle scattering collision operator. We accounted for parallel flows only being carried by untrapped particles. That means particles that can circulate the machine. They're not held in by the magnetic well of going from the outboard to the inboard side. It turns out there's a boundary layer in velocity space that you had to take account of. And all this stuff is very near the separatrix. So the geometry is, near separatrix geometry. And so it's definitely not a simple cylindrical and so forth. So here's the answer, okay? Ugly. It says the particle flux and heat flux are matrix of diffusivities operating on the thermodynamic forces of the pressure gradient with an electric field effect from mobility and a temperature gradient. These diffusivities are, this is actually Brzezinski. This is magnetic perturbation squared, and these are coefficients that integrate over energies of particles. Low energy particles are collisional, high energy particles are much less collisional, and you have to take account of both, and it's effectively a Pade approximation to the analysis to integrate them up in this way. Anyway, long bit. So the role of the magnetic perturbations is very important in these models. Almost everything I've been saying today has to do with delta B over B squared, okay? And you get kink-like responses off the rational surfaces. And the way we're doing this analysis is we're saying, look, we'll use an extended MHD code, in this case M3DC1. We'll find the equilibrium, and we'll apply a 3D magnetic perturbation outside, and we'll ask, as a function of radius through the whole plasma, what are the magnetic perturbations? And then I'll use the I'll use this wonderful analytic stuff to calculate the transport caused by those magnetic perturbations. So in a sense, it's a separation. It's an MHD extended MHD calculation. It's a two-fluid model, it turns out. For the MHD, it gets a set of magnetic perturbations, and then they turn it over to me as the transport analyst guy and say, okay, for these magnetic perturbations, how much transport do you get? And so, anyway, we really should be doing a nonlinear calculation, but that would take a few months, and we have a few cases along that line, and a technical detail we'd like to do a little differently. So this shows you what comes out of that M3D calculation, M3DC1 calculation. What it says is, here's the magnetic perturbation over the outboard midplane. And again, it's this, we're concentrating on only this very, very edgy region of the plasma, 0.85 to 1. And these magnetic perturbations, you remember if the plasma is flowing toroidally a lot, okay, it's going to screen out. It's like a superconductor. It's going to screen out the magnetic perturbations I apply, which are these RMP. Now the RMP applies not one mode, but many. A 13-3, someplace hopefully it says there was these are n equals 3, toroidal mode number of 3. Didn't say that. Anyway, so the blue curve here, or this one, is the n equals 3 perturbation, and it's sort of small at that rational surface. The n equals 2 is sort of small at that rational surface. And I've highlighted the 11-3, which is kind of one of the more critical ones in the right spot. The vacuum level of the magnetic perturbation, if there were no plasma response, is there. But the flow screening kills it by almost an order of magnitude there. But the important thing for a flutter model is not what happens there. It's actually off the rational surface, because the flutter is just the wiggles in between, it turns out. Now, the original models of if you applied these RMPs, what would happen? The original models said, I'll just get stochastic fields over this whole range. And so people did, left-hand side, people did Poincaré plots. And they said, well, I'll follow a field line around toroidally and make a mapping. Every time it comes through that one point, I go around, I'll put a dot here. And so for one particular shot, you know how in wines you talk about it was a good year for Bordeaux or whatever, you know? Well, in a similar way, in tokamaks, boy, this was a good shot. It was 126006 at 3600 milliseconds into the discharge. 126006 was a good shot. It means they got a lot of good data and they believed it mostly and that sort of stuff. Anyway, so modeling that, applying these RMPs to it, what happened was that you got a stochastic field over a huge range. If you did an axisymmetric tokamak and you added vacuum magnetic fields, you got stochasticity over the whole outer range from point A outward. So effectively KAM surface, there's sort of some sort of residual islands you can see in here, magnetic islands. This is radius, sorry, and this is poloidal angle. And so basically you lost all the field lines outside of 80%, and you should have gotten horrendous transport, 100 to 1,000 meters squared per second. On the other hand, if you now took those magnetic perturbations that came out of M3DC1, the ones that are flow screened on the rational surfaces, and create smaller islands, then you get the picture on the right. There it turns out, there's a stochastic region here, but beginning about 0.9, you see strings of isolated sequences of magnetic islands of different pitches as you go along. And what I call magnetic flutter is, if you notice inside of here, I've obviously got effectively some KAM surfaces between these two strings of islands. Hopefully they're going to get some better versions of this. This is a couple of years old. So what we're going to calculate in the quote flutter model is not the transport around those islands, or in the islands, which would be quick across the island region because they sneak through the X points, but rather because of these wiggles. That's what the flutter transport is. Viewed actually in a different way, but that's a technical detail. And so that model I told you about, here was the one I told you, the shot, you know, they don't like it because it's too big an effect, but hey, I like it because I can see whether I've got it. Here, the dotted line is the chi-e, or diffusivity profile, again, over this outer range here, as a function of radius. That's the dotted line. And then when they apply the RMPs, what happens experimentally is they get the blue curve after interpreting the data, basically. And we call this the diffusivity hill. And what it's doing is it's taking, by the RMPs, this pressure profile down, and it stabilizes those edge localized modes, it turns out. So it's decreased the pressure gradient in the right places to cause suppression of, as it's called, of RMPs. And so we then, if we look at our theory says, hey, there's tremendous transport in and around rational surfaces, parallel heat transport, but between the rational surfaces it gets smaller and it kind of asymptotes. So you follow a green curve here is our effective flutter model, it turns out. And lo and behold, it looks like this, but if you, and you can't see it here, but there's flattening of the temperature profile where the chi's are very big on rational surfaces, but it kind of asymptotes to some average radial gradient in between. And so you take the average of that average between rational surfaces, and you get some number here. And like I say, this is what passes for some degree of reasonable agreement between theory and experiment. I think I have another one. No, I don't. Okay, there's another case we did. the one that had these magnetic perturbations, we actually did that case as well, and it also works out. If we put in islands, it turns out there's two islands like those islands of that width, which they're calculated in a funny way. But anyway, if we use that big an island, it's too much, and you get the red curve, which pretty well disagrees with the experimental curve. And so we think maybe there's not islands there, but it's a raging debate at D3D as to whether or not there are really islands in there, or there's this flutter model in between, or there's some degrees of stochasticity. And the problem is there may be a mix of all of that, and that there's dissipative effects that confuse all kinds of stuff. Now, so where in the profile do we care about? And the answer is that it turns out that the chi-e is increased a lot at the top of the pedestal. So right in this region, right about there. And the heat diffusivity, electron heat diffusivity is increased by a factor of 6, and the density diffusivity by a factor of 3. In the edge, you actually get more density diffusivity than electron heat diffusivity. And one thing you always want to check is it proportional to magnetic perturbation squared? And so, and I can't seem to do it. Oh, okay, I didn't show you that graph. Okay, so we checked, and yes, it goes approximately proportional to the magnetic perturbation squared. Okay, so it turns out that this present status of this sort of thing is that we have two cases we've been able to do in detail. It's pretty heroic type data analysis and then transport analysis, interpretive, and then we develop the theory, and then you have to go off and do this magnetic perturbation analysis from the MHD, extended MHD code, and then you put it into the flutter transport calculation. And it works for two cases, okay? Well, it's better than one. But the problem is we really need more. And so this last spring, D3D went through a whole series of experiments trying to figure out, okay, let's really test this model and other models. Let's really test these things, and let's go into the other things. Okay, the ion stuff I was talking about with this neoclassical toroidal viscosity, that was a non-ambipolar ion process. So that caused what's called a counter rotation. These, basically, electrons move so much faster than ions, square root of mass ratio at the same temperatures. So if you wiggle the field lines, the things that are going to move are the electrons. And so that actually is a non-ambipolar electron loss. And so the electric field has to build up positive to try to hold it back. And this is a more subtle effect that we need to be testing in the theory, and that increases the density, diffusivity, and so forth. So we're sort of happy about that. I joke to many people, I used to be a core transport guy, so I worried about transporting the core. And with earlier analysis than this, with the flutter model, we're working at the top of the pedestal, and then I do some work on the edge. But, you know, where we really got to go is the separatrix. So let me go back to this graph momentarily. So when you apply RMPs, and you're in the control room, so to speak, of the experiment, what do you notice most? You notice what's called density pump out. That density went down by a factor of 2, and in particular, over the whole edge region, it went down. And in particular, if you look at the separatrix, the change in density gradient is largest there. So that means right at the separatrix is where you killed the pressure, the density gradient. You actually steepened the electron temperature gradient. But that's easy to understand, because if this happens, then you know, a heat flux is N chi grad T. If chi stays the same, density goes down. I've got to steepen grad T to carry the same amount of heat flux. So it seems like we need to try to figure out why in the blazes does the density change very close to the separatrix. That's not pleasant. So 2 new effects occur at the separatrix that could cause this density pump out. First is that, and I'll show you some pictures of some stuff of homoclinic tangles, lobes. The first is that these 3D homoclinic tangles, they actually, or lobes, they actually cause an additional transport in the region down near the X point of that diverter. And also, some of the field lines out in this region are directly connected to diverter plates. You know, they just go straight there. They don't even circulate. Most field lines in a tokamak just circulate around the torus. So we have to worry about that. Now, this is a side comment I think I won't go into, but there's also debates about what determines the gradient in this region. And it turns out, I believe the situation is that at low pressure, it may be this paleoclassical transport stuff, but at high pressure, and that's where they mostly operate, they get what's called kinetic ballooning modes. They're an ideal MHD instability. Ballooning means they are maximum on the outboard midplane, where the curvature is the worst and most unstable. It's a localized Rayleigh-Taylor instability on the outboard midplane, it turns out. So I don't want to go through that in detail. And I got the wrong figure on this one, so ignore this. And just read some of the words here. It turns out it's really strange. But usually in plasmas, the electron heat diffusivities, radial, are within a factor of 2 or 3 of the density diffusivities. So, you know, you go through all these kinetic models, and they're within a factor of 2 or 3, with chi-e, the electron heat diffusivity being 2 to 3 times the density diffusivity. Well, out here in this steep gradient region, and very, very close to the X point, the separatrix down there, it turns out we've kind of figured out that the effective diffusivity, D, is not, 1 meter squared per second, which is what it tends to be in the core, but it's down to, 0.02 meters squared per second, down a factor of 50. And here we get into real experimental empiricism. Why is that? Well, the best interpretive model, and frankly a paleoclassical theoretical model, is that you have, let's say, 10 units of outward diffusive flux and an inward pinch units of 9 units of flux. And the cancellation gets you very small, is the basic idea. And so the edge region, the edge steep gradient region is kind of funny. But because this density diffusivity is so small, and it's actually only about a tenth, it's actually below 0.1 meters squared per second over this whole edge region. Oh, this is where we were doing a benchmark calculation, interpretive benchmark of many codes. And we were using 1.2, which is a core code, pushing it as far out as we could go. And we were coming in from outside with Georgia Tech edge code, SOLPS, and actually UEdge, UEdge here, and coming from outside the plasma inward. And we're trying to get them to overlay, and we consider this reasonable agreement given the amount of uncertainty in neutral recycling. Anyway, so the basic idea is that a D at this level would affect the density gradient. So, we up it a bit. But the chi-E's, it turns out, are up in this range up in here, so we wouldn't affect them. And so we needed to understand that. Okay, so the basic idea is that we'd like to kind of begin to look at the separatrix, what happens. Now, to develop analytic theory, which is my bailiwick, basically, and trying to relate these to experiment, we're going to have to develop a suitable magnetic flux coordinate system in the X-point region. And so this is a graph from Oliver Schmitz and folks using B2 Irene. Anyway, and they try to calculate the magnetic perturbation levels, or the magnetic field structure down near the X point of the tokamak, the details. And when you do KAM theory and so forth and so on, you see this kind of stuff too. And what's going on? Well, basically, inside the tokamak, the red curves, or the red points, is the Poincare plot. The red points indicate field lines that just circulate around the tokamak and never go out. The blue lines are basically what a guy named Todd Evans, who does this, who started a lot of this, calls the homoclinic tangles, or you might call them homoclinic lobes. But in any case, basically they're lobes like this, and when you put a diverter plate here, you no longer get a smooth where the field lines hit the diverter plate, but you get striations. And they'd like to understand that so they can figure out how badly we can burn up diverter plates, or how we can prevent burning up diverter plates. And so the basic idea is, from a theoretical standpoint, I need to figure out, hey, what kind of I need to calculate plasma transport, not Brzezinski, but, kind of a mixed theory of kinetic and fluid hybrids of transport given this sort of magnetic field topologies. And frankly, getting the MHD codes to work in these X-point regions is itself a challenge. And I think I read that Boniface is going to lead a project trying to figure out how to do that better, because we've got real problems treating the magnetic structure down near the X point with resistive MHD codes, let alone when I add these 3D effects on top of that. So I'll give you a little advertisement if you want help on that, I don't know. Anyway, I'm much simpler, okay? Now, it turns out that, that if you make a transformation from Cartesian coordinates to these ones that that we all use inside the tokamak, which are the ones I told you about, psi, theta, zeta, or rho, theta, zeta. At the x point, okay, at the x point right there, the Jacobian of that transformation blows up. It's infinite because b dot del theta is 0, it turns out. But anyway, and so, but I really liked those coordinates because field lines were straight in those coordinates, in the sense that if I unfold the flux surface, the field lines are plotted, they're straight in a colloidal angle, toroidal angle. And that makes the mathematical analysis a lot easier. Now, there's two types of coordinate systems that people use. If you're in the stellarator community and you're used to ideal MHD, what you say is, I'll put all the magnetic perturbations in the field, and I'll have flux surfaces, which if I have bumps and wiggles, the flux surfaces will follow those. Well, how am I going to get such a coordinate system to work? There. And the answer is, I ain't going to do it. Doesn't work, okay? And in contrast, the axisymmetric system in a tokamak is pretty firm, and the perturbations are only of the order of 1 part in 10 to the 3 or 1 part in 10 to the 4. So, and frankly, if you do 1.5, or these transport modeling calculations, they're all done. 1.5D means it's really 1D, but it takes account of the shape in 2D. Anyway, those transport calculations are always relative to the toroidal magnetic flux surfaces. So we will use a lowest order 2D axisymmetric field plus small perturbations. And this is then viable all the way through the x point. So the model to be used is we'll use a 2D axisymmetric magnetic field, plus we'll add a 3D perturbation. The first step to do this is down near the x point. As I said, this is my depiction of that x point, just simple analytics. We need to develop a good axisymmetric version down near the x point, because down near the x point, right at the x point, my Jacobian of the transformation from Cartesian to these coordinates, straight field line coordinates, blows up. So I've got to do something to kind of really get at that. And then I'll add a perturbation on top of that. So then this is what I tried to sketch over there. So this is my simple depiction of an x point. And if I ask about the axisymmetric magnetic flux surfaces, those are the red lines. And then if I apply a 3D perturbation, I do that. I might say, for people who know about these things having to do with dynamical chaos and Chirikov maps and, the standard map and Chirikov criteria, so forth and so on, this is sort of like one perturbation that goes into that. And effectively, that little line represents, as far as I can tell, what's called a Melnikov orbit. I don't know if people are familiar with that, but it's the mathematics of how you calculate perturbations on a two-dimensional system, or a one-dimensional in that case, but anyway. And however, the Melnikov integral calculates along that wiggly field line. And basically the philosophy, I think, is going to be more useful, but we shall see, is to take the axisymmetric flux surfaces and then add these perturbations. So anyway, I'm going to try to finish a little bit early. So you can, well, it turns out where this x point is, in that x point, or, this x point, that is a saddle point in the poloidal magnetic field. So going this direction, the magnetic field goes up. Going this direction, it goes down. Okay, so it's a saddle point. And so you know, you just say, hey, I got a local Cartesian coordinate, so I'll make it, the poloidal flux becomes a saddle point. And then there's certain characteristic of it, and then this y equals constant is a parabolic equation, basically. Also, there's two forms of parabolic equation, so the gradient of the flux surface dot the gradient of the other type of parabolic coordinate vanishes. And anyway, other people doing this rotate by 90 degrees compared to what I'm doing just to confuse things for me. Or I'm confusing them probably. But anyway, so then you can ask things like, what's the expansion factor? If I'm within 1% of the separatrix up at the midplane, how much do I expand here? And surprisingly, in D3D, the numbers are sort of like you might be a half a centimeter away from the separatrix at the midplane, but you're like 15 centimeters, 13 centimeters down here above the x point. An expansion factor of 16 or so. Anyway, and then you can follow a field line. You just dx, dl, x being the position of the field line, dl for any vector field following it as b vector over b. You take its components and you say, well, there's some parallel length over which things vary. You can calculate the field lines, and I missed a logarithm inside of here. So you can say how long are the field lines. What makes the analysis kind of interesting and complicated is that when you're way up here, so to speak, field lines as they go around toroidally have a pitch. When you get very close to the x point, the field lines are almost only moving toroidally. So you go from a field line that's twisting down to one that only goes around toroidally like this. And then as you go below the x point, then they wind up again. So calculating the actual length of a field line is a little tricky. And it can be comparable to the collision length. So maybe we can get back to Brzezinski after all, okay? Because you remember our Brzezinski condition was that we had to have a short collision length compared to the inhomogeneity length. Well, very close to the separatrix, we turned out to have collision lengths that are only about 10 meters in contrast to 1,000 meters or so. And, you know, field lines are getting to be 20, 30 meters, 50 meters even down there. So we get a mix of collisionless a little ways away from there and collisional right near the x point. It's going to make the analysis fun. Anyway, so there's these various things of calculating a poloidal angle. Usually the poloidal angle is just almost like the poloidal angle in the cross section. So, you know, it's just like the angle around here. But it turns out it's logarithmically divergent down near the x point. So you have to transform your coordinates and take account of that. So then you can ask the question, okay, so I will claim I got a simple description of that red line, which is a magnetic flux surface, axisymmetric magnetic flux surface. Now I'll try to add some resonant magnetic perturbation. And you just go through the math. And if you calculate, well, how big a wiggle do I get in radius of the axisymmetric surface? It's just a b tilde over b times how long I go. And if this is not resonant, you know, you get a characteristic number, and basically that's a small wiggle in the field line. However, if I'm resonant, then it turns out that then I go a long distance along the field line in resonance here. And so I get 1 over m minus n q, it turns out. And so I get a bigger excursion. And the nature of the exercise I'm playing with at the moment is just, okay, can I get as big a perturbation as was seen in this diagram? You know, that's sort of 10 centimeters or so, turns out. And the answer is, yes, I can sort of fudge the numbers and make it work, okay? That's sort of where we are. I got about 7 centimeters. And then you can say, well, if I have one of these flutter type models, how much transport will I get? And the answer is that, oh, I can kind of get 1/10 of a meter squared per second by a suitable set of fudge numbers. I say a suitable set of fudge numbers because when you do these calculations analytically, and you do them for the first time, what you do is you say, hey, am I in the ballpark here? Is this even going to possibly work? And so you go through and you sort of make some sort of, I'll guess that parameter and so forth and so on. And then, you know, if it's worth doing, then you do the hard work of really doing it. And I'm only at the first stage. Oh, okay, I can maybe make it work. So in summary of these RMP effects, they depend upon the pedestal region. At the pedestal's top, okay, up there, the flow screening together of these externally applied resonant magnetic perturbations, 8.3, 9.3, 10.3, 11.3, 12.3, 13.3. Anyway, they seem to give about the right amount of transport to explain the amount of reduction of pressure gradient in this edge region and hence the stabilization of these so-called edge localized modes. In the steep gradient region, you know, in this region, the very steep gradient region here, there may be a mix of at low beta paleoclassical and high beta kinetic ballooning modes that a guy named Phil Schneider works on quite a bit and so forth. And I'm trying to work on this business of extra transport effects at or very close to the separatrix. And it's going to be a mix of these parallel transport along open field lines, which may be in a collisional, believe it or not, Brzezinski regime, and a collisionless, just to complicate analysis. And these homoclinic tangles or something may cause additional transport of about the right level to explain that density pump out at the edge. And the experimentalists are harassing us pretty hard. Give me a formula that they can test. And any formula that has more than about 3 parameters in it, they don't want to see. So you have to kind of simplify it. But anyway, and then do more details. Okay, oh, I forgot a couple of things. So suppose in the plasma here, on the 2-1 surface, I put in a resonant perturbation and I lock the mode and the toroidal rotation to 0 at that point. Okay, what happens? Well, experimentally, it turns out they did that. So imagine that this is in NSTXU and about halfway out in the minor radius of the plasma. They turned on a resonant field and they got a delta, they locked a mode there, and so they immediately started affecting the rotation in this region, and then as a function of time, it diffused in from the side. In contrast, if they used a non-resonant perturbation, it was just the whole plasma sagged. It was not a resonant effect. And so you could see the resonant effect versus the non-resonant effect. Did the pitch of the external fields resonate at that rational surface or not? So now I'd rather finish rather quickly here. So let me just say, ITER keeps asking, okay, how much of a magnetic perturbation do we need to put in? And so we give them some guidelines, or I don't, but the experimentalists do, and with some listening to what we say, but pragmatically it's their empirical experience mostly. And then they do one other thing. ITER is really not going to produce any power, okay? That is to say, it's net power, net electrical power. Rather, what it's going to do is try to demonstrate that you can get more energy out than the energy you're putting into the plasma. 50 megawatts of external heating, you hope to get out 500 megawatts of fusion power, most of 50%, 80% of which is in neutrons that go out. And the first director of ITER was a Japanese guy who had been in the fission power industry. And he said, well, I think we ought to have a test blanket module in there, so we'll absorb the neutrons in this test blanket module and see if we can produce little tritium and stuff like this. And so what they did is they said, we'll put in one test module. what does one test module do to the magnetic perturbations? It introduces a delta function in magnetic perturbation, or actually a dipole, it turns out, but anyway. And so you get a whole spectrum of stuff. You know, you take the Fourier transform of that, and you get a whole broadband. And they did an experiment then on D3D, and they found that, lo and behold, what do you think is going to happen? You get a whole spectrum of modes. Whichever one couples to the least stable MHD mode in the plasma will get excited. And that's the n=1 kink mode. So even though it's a delta function in space, it actually couples fairly well, unfortunately, to the least stable MHD n=1 kink mode in the plasma. Pragmatically, they've done some tests, and yes, you affect mostly the toroidal rotation, much less by factor 3 or 4 the heat transport or the density transport, and that it's at a tolerable level, and they plan on putting in 3 of these modules rather than 1, so your minimum will be n=3 maybe, or something like that. Anyway, so I won't go through that, but the basic idea is that's what's happening. Now, so all these effects are important for ITER because they want to rotate the plasma so as not to get penetration of field errors and maybe be able to control the toroidal rotation. And I've just been telling you a little bit about all the kind of funny things that can happen. So anyway, so kind of a summary of the status, issues, and research topics of this area are that the 3D field effects, the transport evolution equation for the toroidal rotation, including these 3D effects, is available. Here it is. And NTB theory is sort of validated. Toroidal ripple is validated. Resonant effects. And these are all currently still being worked on. And the resonant amplification you get via coupling to the least stable n=1 edge resonant kink modes. Field errors. So kind of the status is the combination of these 3D effects with extended MHD responses and instabilities is being developed, and the neoclassical tearing modes and everything interacts, and the RMPs, we're trying to figure out how all this works, and the 3D effects mostly are on the toroidal rotation, but then that may affect the density and electron temperature transport. Possible research topics, we really need, I would suggest, a self-consistent theoretical framework for combining kinetics, which I have to do now by analytics and stuff, with extended MHD models and plasma transport equations. And so here's my, again, major, from my perspective, the kind of themes of these, not just my lectures, but everybody else's here, I think. Or at least Vladimir, anyway, Vladimir's. So 6D kinetics is basic. Okay, that's the fundamental place we start with the plasma kinetic equation. But for times longer than collision times, 3D fluid moment equations are feasible, appropriate, and very useful. I claim that they can be made exact relative, back to the kinetics if a relevant Chapman-Enskog kinetic equation can be solved for the kinetic distortion, and the results produce fluid moments and closures from that. The plasma kinetic equation is dominantly a first-order hyperbolic equation and got Hamiltonian orbits, beautiful Hamiltonian theory you can use, with a weak parabolic equation effects due to Coulomb collisions, which are down, 6 orders of magnitude from the plasma frequencies and so forth. And so you kind of need both resonant phenomenon at fast speeds and fluid stuff at long times. And so the ultimate challenge to me is somehow effectively determine 6D green functions that allow you to capture both small time diffusive scattering in velocity space together with something that then allows us to get the right answer on the long time scale. And I was encouraged to see Eric's stuff about collisions because in the US, I keep bugging the gyrokinetics people about collisions, and they don't give me very satisfactory answers, but I felt like I was getting some satisfactory answers about, yeah, you're working on it and it's getting there, which is great. But then we got to be able to couple that into the long-term scale, long time scales. My way of suggesting for, as I call it, a grand unified, very modestly, of course, anyway, a grand unified tokamak simulation for developing a predictive capability for ITER would be a small gyro radius expansion for the tokamak. That allows us to do a lot of things beyond Brzezinski. And then we treat the various physics involved in, should say, radial, parallel, and toroidal components of the force balance equation. And I would focus on extended MHD to obtain the detailed magnetic structure, including singular reconnecting regions, externally applied 3D fields, stochastic fields near the X points, and so forth. And then that we would turn over that magnetic geometry, special details, let me put it that way, in a Chapman-Enskog kinetic equation in that distorted geometry, and obtain the combination of collision-induced and microturbulence-induced gyrokinetic anomalous radial transport. And then, frankly, then we have to go back and iterate and say, well, now I changed the diffusivities and the transport, and so I go back up to here, and we have to iterate. That's a long-range vision. Who knows if we'll ever get there, but at least as a construct, I'd like to believe that's in the right direction. Let me put it that way. So hopefully we have all entertained you, so to speak, for a couple of weeks. And I'd just like to say on my behalf, and I think all of the lecturers, it was wonderful that you invited us all. The only complaint we have is that Eric nearly ran out of voice this morning, and, and these 2-hour lectures are a little longer than, no. But anyway, I think we did, we all appreciate what Boniface has put together for this. Thank you. This is a bewildering bunch of stuff.
Do you have an idea on this? Because when you see you calculate only the microturbulence in a perturbed way to put it to the MHD code, how much this would be reduced as compared to solving with the full gyrokinetic equations? Where do you win by it?
I tend to view the gyrokinetics equations as probably only able to handle a little bit longer than a collision frequency. And these tearing modes, for example, grow on very long time scales. So collision times, you know, would be, most gyrokinetic codes now tend to operate only for, say, 100 microseconds or something like that. And even in present experiments, resistive tearing modes grow in 20 millisecond time scales. And plus, the big thing, the extended MHD codes deal very carefully with all of the magnetics, and the transport codes deal with all of the sources and sinks, neutral beams, electron cyclotron current drive, all that sort of stuff. And to me, the microturbulence handles one of the most critical up towards the top of the pedestal, which is the transport in the core. But it doesn't probably want to deal with all these other things. So that's the reason why I tend to separate them.
Other questions?
No. Exercising.
Everybody's tired now, and so thank you again.
Thank you.